Well, good evening, everyone. I'm David James, and I'd like to welcome you to this Institution of Engineering and Technology Sussex Network talk. So now to introduce our speaker. In fact, I'm very pleased to welcome Professor Mark McCaughrean. Mark is the Senior Advisor for Science and Exploration at the European Space Agency. He's also responsible for communicating results from ESA's astronomy, heliophysics, planetary and exploration missions to the scientific community and the wider public. After studying at the University of Edinburgh, he worked for the NASA Goddard Space Flight Center, astronomical institutes in Tucson, Heidelberg, Bonn and Potsdam, and the University of Exeter before joining ESA in 2009. His scientific research focuses on the formation of stars and their planetary systems, and he is an interdisciplinary scientist for the NASA ESA CSA James Webb Space Telescope, more of which I'm sure we will be hearing in a little while. By the way, Mark is also the co-founder of Space Rocks, which celebrates space exploration and the art, music and culture it inspires through public events and more. So welcome everyone and welcome Mark. I'll stop sharing my screen now and hand over to you.
Thank you very much, David, and good evening everybody. It's a pleasure to be here. Let me just go ahead and share my screen. Should be okay, is that right, David? Good. Yes. So thank you very much for the invitation to speak to the Institute of Engineering and Technology. And as David explained, I'm the Senior Advisor for Science and Exploration at the European Space Agency. As you can see from my fake background, I live in the Netherlands and I work at a place called ESTEC, which is where roughly half the people in the European Space Agency work. Of course, we're spread throughout Europe, including in the UK, France, Germany, Italy, Spain, and so on. But as I say, I'm based at ESTEC. I haven't been there that much for the last 2 years. It's just 12 kilometers up the road. So I've done a lot of talks from my shed here out in the garden. But this evening, I'm going to talk about what we do in space science and human and robotic exploration. And these are the two areas where I work in the agency. But we have much more that we do, of course, telecommunications, navigation, Earth observation. And I'll talk about some of those things during this talk this evening. There's too much material to go through in 45 minutes to an hour. And I'll be skimming over many things, but please, if there are questions, do feel free to put those in the Q&A, and we can have some time at the end. So let's just start by dialing back just over 60 years now, so to the beginning of 1961, just a few weeks after I was born, as it turns out. Yuri Gagarin was the first human being to go into space, and then just a couple of years later, Valentina Tereshkova, the first woman to go into space. Of course, the space race that began in the 1960s between the Soviet Union at that point in the United States led to a lot of advances in human spaceflight, as we'll see, but also in robotic and space science exploration of the solar system and the universe. But just to see where we've come in those 60 years, here is Gagarin's return Vostok capsule, the descent capsule. Of course, he didn't actually land in this capsule. He ejected from it at quite high altitude and came down under parachute. But you can see the level of the technology from 60 years ago. And just fast forwarding to today, this is where we are. This is the exterior of the International Space Station. 2 astronauts, one from Europe and one from Japan. So not only, of course, is it the United States and today Russia, but a fully international space station. And what you see here are these 2 astronauts putting new solar arrays onto the main truss of the space station. So we've gone from that small capsule to this enormous football field size structure in space. And I just thought I would talk a little bit about some of that before going into the space science. But I also wanted to start with this picture taken from the space station by Thomas Pesquet, ESA astronaut last year. And this actually nicely shows a view from where I live on the Dutch coast in a place called Wassenaar, where I'm sitting now, all the way across, of course, the North Sea and the Channel to England, Wales, Ireland and Scotland. And in honor of it being in Sussex, I thought I would point out that I actually lived in West Sussex in the 60s and 70s in a small village called Milland. You can see all the places I've lived in the UK. I've actually spent half of my life now out of the UK in the US and in Europe. But it's not that far across the North Sea. Let me now show you another video, a video in this case taken by Thomas Pesquet, this time over New Zealand in the middle of last year. And this time lapse shows the Aurora Australis, and it's approaching the dawn as we go up across Milford Sound here in the corner. So very beautiful. You can see the air glow in the upper atmosphere, the orange glow, the aurora above that at 100 to 150 kilometers altitude. But I'm going to stop there, and now I'm going to zoom in to the top right corner. And what you're going to see now is, as we approach the dawn, hopefully on zoom you'll see a number of streaks moving from left to right across the field. And these are objects in low Earth orbit. They're satellites, most of them. There may be some space junk among them, but there's a colossal number of satellites up there now in low Earth orbit around the altitudes of the ISS. And in fact, if you take just one still from that and look, what we know by having figured out exactly where we were on the ISS at the time, what the time was, and what the orbital elements of other satellites were. At least one of those objects is a Starlink satellite, this so-called mega constellation of low Earth orbit, if you like, Wi-Fi routers, in principle giving Wi-Fi or high-speed internet access from low Earth orbit. Of course, this is becoming a problem because not only is Starlink being built, but we also now have OneWeb starting up, Project Kuiper from Amazon, and a large number of other potential low Earth orbit missions providing a dense network of high-speed internet from space. But these are the same orbits that are occupied by many of our ESA assets, whether it be the ISS, whether it be Hubble Space Telescope and other astronomical missions like Hinode, Chaops and Proba 2, but also Earth observation assets, Sentinel-1A and B, 5P and Aeolus, the mission looking down at the winds. And so this is becoming a big problem for traffic in low Earth orbit and debris, but also for astronomers using low Earth orbit as well as astronomers using observations from the ground. So these are a series of images taken by the Hubble Space Telescope in the last few years, taken as postage stamps. And these are all satellite trails moving in front of the Hubble field of view. And because Hubble itself is in low Earth orbit, some of the objects it's seeing are very close by, within 10 kilometers or so, and grossly out of focus, which you can see in the streaks in the bottom part of the screen. And this is becoming a problem because when you quantify the number of satellite trails that you see over time, and we did this with a group of young graduates, undergraduate students rather, working over the summer on a project looking through the entire Hubble Space Telescope imaging archive for more than 12 years, the statistics you see are quite worrying. So what we're seeing here is the chance of seeing a satellite crossing the field of view in roughly a 10-minute image, an 11-minute image. And you can see that between 2009 and 2020, that's been rather flat. But in 2021, when a substantial number of these mega constellation satellites, mostly Starlink, were launched, we see a large increase statistically. So going from 3.5% baseline on average up to 6.5% chance of seeing a satellite crossing your image. And again, some of those are very hard to get rid of because they're very wide, out of focus. And this is just the beginning of the mega constellation era. And so it's becoming a worry for astronomers who work in low Earth orbit. As I say, most of those are probably linked to Starlink. You can see the very rapid rise in Starlink satellites. Strangely, it's quite difficult to actually definitively identify the Starlink satellites because they move around a lot in their orbits in order to avoid collisions with each other and other low Earth orbit assets. So actually putting the finger on a Starlink satellite and saying that's what it is tricky, but statistically it has to be them at the moment. So let's step back from that and look at the ISS from the outside. This was an image taken in November, just at the end of last year, on a fly around in capsule returning to the Earth. And you can see this astonishing large structure with several laboratories, many different modules for science, for habitation, for engineering, and experiments bolted to the outside on the main truss as well. And on the inside, this is Samantha Cristoforetti, one of our ESA astronauts. She flew in 2015 to the ISS, and she's returning in a couple of months' time, going back for her second long-duration flight, for 6-month flight. And you can see, of course, that they have to keep fit on board in the microgravity environment. So there's Samantha running on a treadmill. I'm not sure exactly what she's watching on the laptop, but I do know that she watched the entire series of Battlestar Galactica when she was there on her last mission. So they get some downtime, some entertainment as well. But because humans live on the ISS, on the interior, there is, of course, an ecosystem, a biosphere, if you like. And one of the problems with that is, over time, the accumulation of bacteria. And you can see on the left-hand side here, in 2004, a wall behind one of the modules. You can see mold growing on that wall. And if a more recent survey done just a couple of years ago, looking at where throughout the ISS different bacteria are seen, you can see there's large complex of them. And in fact, some of them have evolved on the ISS in that closed environment. And that's led to some rather silly scare stories about new life forms being found on the ISS. These are all ground-based bacteria, not alien life forms, but they can develop in that closed ecosystem. So a lot of these headlines are quite interesting in the way that they stress the problem. But of course, we have to work with it and think about how we can keep the ISS as clean as possible. And looping back to last summer, this is in my back garden, which is just on the other side of the lights here. And I spent quite a bit of my free time in the summer photographing dragonflies. And what I didn't realize at that time is that dragonflies, which almost always have very clean wings, they actually have a very clever nanostructure property on their wings, which prevents the formation of bacterial films. And so what you see here is the nanostructure, which is on a dragonfly's wings. And you see E. coli bacteria effectively rupturing themselves on those nanostructures as they try to move around. And these nano-textured surfaces are important, possibly in long-duration spaceflight environments like the ISS. And what the experiment I'm about to show you combines the nanostructure and copper. And copper has well-known antibacterial properties, although not fully still understood why it's antibacterial. So the experiment that we're doing on the ISS at the moment is in this box. This is Luca Palmitano, another ESA astronaut. This box called Kubik can just have materials floating in microgravity, so just in the ambient environment of the ISS, but it's a centrifuge and it can spin materials up to Earth gravity equivalent or to Mars or the Moon or others. And what's being tested in this particular experiment called biofilms is looking at interference-generated etched structures on metals, so steel and copper and other materials, and looking at how the etching density, the wavelength of the etching, affects the possibility of bacteria being able to exist there happily or get ruptured as they are on the dragonfly wings. And you can see on the bottom left corner a variety of materials, so steel, copper, and copper zinc, and different wavelengths of these structures, the periodicities. And you can see the bacteria that are currently being tested on board at the moment. I have the results for you. This is a very recent experiment flown up last year. So this is the kind of thing we're looking at on the ISS. Of course, not only in terms of being able to potentially use antibacterial surfaces on the Earth, but looking at long-duration spaceflight, because we're now moving back out of low Earth orbit, and in particular, in the near term, returning to the Moon. So, of course, I showed you Gagarin and Tereshkova at the beginning of the space race in 1961. This is another seminal moment in that space race, 1969, where Buzz Aldrin and Neil Armstrong landed on the surface of the Moon. And of course, the Apollo program ended in 1972, and no humans have been back to the Moon since. Well, that's about to change through this program, this is the Orion crew vehicle, which will be sitting on top of the SLS, the Space Launch System, a very large new rocket that is nearing its first test flight in the coming months. A mission called Artemis 1, and it will be carrying this on the top. you can kind of recognize an Apollo-like crew capsule on the top, and then there's the service module below, which you'll remember from Apollo as well. But in this case, it's been provided by ESA. So the European Space Agency has adapted the automated transfer vehicle that we use to send cargo to the ISS, and it's now the back end of the Orion vehicle. So this is the first time that NASA has allowed any other agency to be, if you like, in the critical path for its human exploration. And I think that's something that we're very excited about. Going back to the moon, not just for trips to go around in orbit in Orion, but we're also now working with NASA, with Canada, with Japan, and with Roscosmos in Russia to build this. This is the Gateway. And the Gateway is, if you like, a miniature version of the ISS. It won't be permanently crewed, so maybe months at a time, but not permanently, as the ISS has been for more than 20 years. And also using this as a staging post in this high elliptical lunar orbit to go back down to the surface. And so this is something where we're already cutting metal. We're building components in Europe, in the United States, in Japan, and in Russia. And so this is actually coming quicker than many people think, and will be a very interesting new way of working at the moon. And when we think about the surface of the moon, we don't really want to go back to the same sorts of places that we went before. We want to go back in particular to the South Pole. The South Pole is very interesting because there are deeply shadowed craters on the moon which never see sunlight. And we know that there is water ice in those craters, deposited probably by comets and asteroids, not primordial material, but it's still accessible, we believe. And so if you fast forward to the future, we can look at potentially bringing water ice up from the permanently shadowed craters near the south pole of the moon in a base somewhat like this. So this is what we call in situ resource utilization. So getting the ice directly is one way of doing that. But in the meantime, what you can also do is use rocks nearer to the equator. And so this is Harrison Schmitt, who's a geologist, the only geologist who went to the moon in 1972. And we know from the minerals brought back, which are still being analyzed, still being looked at today, that lunar material includes a whole range of rocks, as you can see there, rock substances. The one I want to pick out there is this one called ilmenite. So this is iron titanium oxide. And if you look at where ilmenite is, it's, well, that's actually, for me, it's hidden. These are the minerals. And of course, oxygen is there as a big component of all of those minerals. Ilmenite's important because it has a high fraction of oxygen, and there are places where this titanium dioxide exists on the surface of the moon in greater abundance, as you can see in this ultraviolet map of the moon here. And this ilmenite can be crushed, and by passing hydrogen gas over it, as has been done in experiments at the Open University by Hannah Sargent and her collaborators, you can extract water. So by passing hot hydrogen over ilmenite, you end up with water coming out of the other end. And that water, the amount of water you get out, the oxygen yield, which then combines with the hydrogen to make the water, is a function of the amount of ilmenite in the base sample that you have. So by going to ilmenite-rich regions, you can get water before we might go to the South Pole and set up a more permanent base there. So now let's move from the human exploration and nearby and move to elsewhere. So this looks a little bit like the moon, but it's actually Mercury. This is the nearest planet to the sun, roughly a third of the distance that we are from the sun, and of course gets extremely hot. It's also a very strange body because our models of how the solar system form don't predict a rocky body of that kind, of that very high density, close into the sun like that. So Mercury has been the target of just 2 space missions to date, and we are now on our way with a third one called BepiColombo. And this is a collaborative mission with the Japanese space agency, JAXA. It's a huge spacecraft, 6.5 meters tall. There's actually 3 spacecraft there. The bottom half is a propulsion module. The central part is the European Planetary Orbiter, and the top at the part behind the cone is a magnetospheric orbiter, which is coming from the Japanese. And what you see here in this picture is the acoustic lab that we have, the acoustic chamber at ESTEC, 12 kilometers up the road from me, and that blasts our satellites with the sound of the launch, so the acoustic signature of a launch, in this case on an Ariane 5, and that simulates the vibration and the acoustic environment that the satellites have to survive. So this mission was launched successfully at the end of 2018 and has been on its way through the solar system using flybys at Earth, Venus, and now at Mercury itself in order to slow its orbit down to go into orbit around Mercury. Although Mercury's close to Earth and you can get there relatively quickly, the real problem is slowing down when you get there, because Mercury is deep in the sun's gravitational well, and that pulls us in. So we need to slow down, and we're using these flybys to do it. So at the end of last year, we had the first flyby at Mercury by BepiColombo, the first of 6, which will get us finally into orbit around the planet in 2025. But I thought I'd show you a film of what it looked for the first time with BepiColombo to actually be at Mercury. So there's a little film with some music here. So you can see the first flyby took place there, and all of the images were taken from the departure, effectively. We flew in from the night side over the terminator at Mercury and looked back at it as we flew by. And the next flyby is in June, so coming up this summer. And as I say, a sequence of 6 in total before we finally go into orbit. And trying then to understand from very close in, so roughly 400 kilometers altitude above the surface of Mercury, where we're sandwiched between the sun on one side, 10 times brighter than it is here at Earth, and on the other side, an object, Mercury, at roughly 450 degrees Celsius, so the temperature of a pizza oven. And the thermal control of BepiColombo is incredibly important to prevent it getting overheated, which is why it's wrapped in that silver material that you saw. Another satellite which we launched actually at the beginning of 2020, which has a great thermal challenge as well, it's called Solar Orbiter. And Solar Orbiter is a joint ESA-NASA mission, which goes in even closer than Mercury to the sun. But in this case, it only is faced with the sun, so it doesn't have to have a full thermal shield all the way around it. Just has this very thick shield on the front, and the windows which you can see on the front of the shield that the instruments can look out through, but when the shutters are moved out of the way. And this is the launch that NASA provided back in February 2020, and because that coincided more or less with the beginning of the pandemic, all of the commissioning of the satellite was done with teams around Europe and the United States, all operating remotely. So even the mission control, people weren't able to go there most of the time, apart from the key personnel. Most of the commissioning was done remotely in the way that we're talking this evening, and that's a great testament to the flexibility of the teams that they were able to do that. So Solar Orbiter has also now flown past Venus a couple of times in order to wind its orbit up and go into a more elliptical orbit, which takes it close to the sun and then back out again. And it recently had a flyby at Earth, its one and only flyby, and that was somewhat hazardous because it had to fly through that low Earth orbit region that I talked about at the beginning, and all of the satellites and all of the debris there. Fortunately, we passed through without incident, but certainly it was quite nervous. People were quite nervous at that point. So now, post that, we're entering the real science phase of Solar Orbiter, but some results from early on, from an early pass, have already shown the power of Solar Orbiter getting closer into the sun with imaging instruments than we've ever had before. And what was discovered on this first pass were these so-called campfires, or more technically nano flares. So very small flares in terms of the solar physics, the size of the sun, but you can see still very large compared to the size of the Earth. And these flares erupt from linked to magnetic field lines, basically breaking as they twist and combine. And you get this flare of energy at very high temperatures, up to 1,000,000 Kelvin, releasing energy and, we think, heating the upper atmosphere of the sun, the corona. The temperature of the corona of the sun is much higher than normal theories would predict, but we believe that these campfires, as we're calling them, may provide the answer to that long unresolved problem. Now, we also not only looking at the sun, but we look out at the solar wind, and we have this rather lovely imaging sequence that was taken in November 2020, where you can see Venus, Earth, and Mars, of course, at different points in distance away from Solar Orbiter across the solar system. And indeed, you can even see Uranus there off in the distance. And this was just briefly after the second Venus flyby of Solar Orbiter, so which is why Venus is even brighter, say, than the Earth in this picture, quite close to Venus. So let's go back to the sun for a moment. There are many unsolved problems about the sun, but of course, which Solar Orbiter will investigate, one of the key things, of course, linked to the sun is space weather, and how the massive coronal mass ejections throw material out into space. These are data taken from SDO and our SOHO observatory, which sits close to the Earth. And you can see these giant coronal mass ejections, which can then interfere with satellites, interfere with power lines on the ground. Take us back to the famous Carrington event in the 1800s. If we had one of those large solar flares hitting the Earth, which we will at some point, that poses great problems for our electricity grid in terms of overload in that grid. But the other interesting point is, of course, how that solar wind interacts with our magnetic field, which is a complex structure driven by the internal dynamo of the Earth, with a bow shock, the so-called magnetopause and magnetosphere, and then the tail, which streams out behind. And we've been studying that for many years with our cluster mission, a group of 4 satellites, which can be at different distances in the Earth's magnetic field, whether in front of the bow shock, in the bow shock, or in the tail. And it's been joined in recent years by another trio of small satellites called Swarm, which operate at lower altitudes, where they have this rather more streamlined look to avoid the problems with atmospheric drag at high altitude. And one of the phenomena which I showed at the beginning, of course, which is very fascinating about the way the material flowing from the sun interacts with our magnetic field, is the aurora. So I showed you the aurora australis before over Milford Sound. This is the aurora borealis over Iceland in 2015. But the aurora is actually a fairly universal phenomenon in the solar system. And in fact, in many of the planets and moons, you can either directly image an aurora interacting with the upper atmosphere. So, for example, Saturn and Jupiter very easily. You can see a more general glow on Mars, and you can see in scientific data evidence for auroral emission around some of the other rather large moons and planets. And even we have evidence around a very low mass star at great distance from our solar system. We have evidence that there's an aurora there as well. But perhaps one of the most unusual places we've discovered evidence for an aurora in recent years is around comets. So again, thinking about the pandemic, hopefully many of you had the opportunity, if you live in the Northern Hemisphere at least, to see one of the brightest comets we've had for many years in the North, Comet Neowise, which was in the summer of 2020. And this is from the beach, just a couple of kilometers from my house. It was very lovely to see. It's been a long time since Hale, Bopp and Hyakutake were in the Northern Hemisphere, so this was great to see. But the comet where we discovered an aurora recently is perhaps even more famous because it's Comet 67P Churyumov-Gerasimenko, the comet that our Rosetta mission was in orbit around from 2014 until 2016 and is now sitting on the surface of this comet. And we followed this comet in from the orbit of Jupiter inside the orbit of Mars and saw this material flowing away. So this is water and CO2 and CO flowing away to form the coma and then the tail of 67P. And I'm not sure if anybody had the chance, but it actually came back very recently. It was visible just a few weeks ago, 6.5 years after the last perihelion. So it will be back again, and we will see it more times in the future. But what we saw was rather interesting in the data taken by Rosetta. And that's that the water, which is spewing away from the comet when it's close to the sun. So here's a water molecule, interacts with the solar wind by solar wind electrons streaming in at high speed, getting accelerated close to the comet, kicking out, in this case, a hydrogen atom, which is in excited state, and then when it de-excites, giving out auroral emission. And similarly, another electron might come in and split the water, this time liberating the oxygen atom, and at a different energy level, being excited and giving out an oxygen photon. So this universal phenomenon, this is in the solar system, but this is the only place where it's due to water and solar wind electrons occurring. In other places, it's different interactions with the solar wind. So a lovely new phenomenon discovered after the mission ended in 2016. And just as a reminder, not only is Rosetta on the surface, but of course, rather famously, so is the small Philae lander, which is on the far right-hand side of the picture, where it was found in September 2016, more than 2 years, just 2 years after it landed and bounced on the surface. If you remember that rather dramatic adventure we had for 3 days back in 2014. Now, comets, of course, are there are many different bodies of comets, many different families of comets, some of which are trapped in the inner solar system, some of which fall from great distances in the so-called Oort cloud beyond Pluto and out for even further than that, the Kuiper belt and then the Oort cloud. And we believe now that we have discovered the first objects which have traversed the solar system, which actually came from other solar systems, so interstellar comets. The first one of those was Oumuamua, and the second Borisov, discovered in the last few years. And so we've now started building a mission called Comet Interceptor, which will actually go and loiter out at the Sun-Earth L2 point, 1.5 million kilometers away from the Earth. And it will wait there, loitering until a suitable target is spotted far enough out that we can then push Comet Interceptor out of that position onto an intercept trajectory, not to go into orbit around the comet, because that would be impossible dynamically, but to fly past it, much as we did in 1986 with Giotto and Comet Halley. And if we can indeed get one of these right interstellar objects, measure the properties of a comet that's come from a completely different solar system. So that's really quite a remarkable advance in the last few years. We're also building new missions at the moment to explore elsewhere in the solar system. We have new missions which will be going to Venus in the future, but this is the one that's going to launch next. It's called the Jupiter Icy Moons Explorer, or JUICE. It's got huge solar panels so that it will be powered by the sun, not by nuclear fuel, at Jupiter, and importantly at Ganymede, Callisto, and Europa. And that spacecraft, this is a picture I took last summer at ESTEC, again in the test center. You can get a sense of scale, and this is without the solar array. So it's a very big spacecraft, and it too will have a fairly long sequence of flybys when it launches, either later this year or the beginning of next year. So there's an awful lot to come from that. It will take a few years to get there. Again, we're not going on a flyby. We're actually going to go into orbit around Jupiter, and that takes flybys around other planets in order to get our trajectory wound up. But Jupiter's an interesting planet because it's representative of many of the planets that we know exist now around other stars, so-called exoplanets. And in this case, this is an artist impression gallery of what some of those objects might look like. But each one of those objects is a real object discovered in various surveys in the last 25 years. So the radii are probably correct. And whether they're gas giants or rocky planets, that's probably correct as well in many cases. But to illustrate the diversity of the families of exoplanets that exist out in our Milky Way, these are all the objects that have been discovered, but we're now beginning to discover more and starting to characterize them. So these are 4 missions, 2 of which are now in orbit. Chaops, a small mission which is focusing on known exoplanets, and measuring the light curve of the background of the star in the system very precisely as the planet moves in front of it. As the planet moves in front of the star gets just a tiny bit fainter for just a few hours. And by measuring that curve, that light curve, you can deduce the radius of the planet. And knowing the mass from other measurements, then we can determine the density in great precision. So we can work out whether they're gas giants, rocky planets, ice giants. And so Chaops has been up there since the end of 2019 and doing extremely well. I'm going to show some results in a moment. But also now joined by the James Webb Space Telescope, which is now in commissioning. And it's going to be doing science similar to Ariel, which is for launch in 2028. And that's doing spectroscopy of the atmospheres of planets, which we know go in front of their stars. So not just measuring the radius, but actually measuring the atmospheric properties as light is absorbed in the atmosphere coming from the star. Different amounts of light absorbed at different wavelengths tells us the spectrum of the atmosphere and therefore what's in it, the contents. And then in the bottom left corner, you see Plato, which is a mission with lots of small cameras covering a very wide field of view to discover new exoplanets going around nearby stars. And those will be perfect targets to look at, potentially probing down to terrestrial mass planets in orbits similar to the Earth around the sun. So potentially habitable planets. So let's just talk briefly about Chaops and something that it's done. So this is a ground-based image, a fisheye lens picture from the European Southern Observatory on Cerro Paranal in Chile with a laser guide star looking at a point in the sky. This is actually an observation of a galaxy that it's doing there, but it's very close to a place on the sky where Chaops has been studying. In this field of view, a very nondescript small target called TOI-1 to have planets going around it. And here is an artist impression of one of the planets nearby, the star, and this family of planets close in. And what Chaops has been able to do is study each of those transits as the planet moves in front of its star in much more detail and give us a much better handle on the radii and therefore the densities of those planets. So here you see the array of those 6 planets around this star, which is just a bit fainter than our sun. And we can derive the parameters, the period of rotation as these planets go around. You can immediately see something is interesting because these planets are going around in days, not in weeks or months or years, but in days. The masses are from roughly an Earth mass and a half up to several Earth masses. The radii we can measure from the Chaops data, and that tells us the density. So a couple of these planets have densities similar to the Earth, and the others are lighter, so are gas-dominated planets. So we've got that evidence. There's the density of the Earth-like planets or the terrestrial type planets. Those are the Jupiter-Neptune type densities. But what's also interesting is these are very close into their star and they're in a resonance. These planets are not orbiting freely around, they're actually locked in a resonance. And if we look at that in more detail, so we're going to zoom out and show where these planets would lie in our own solar system. So there they are. If we overlay our solar system on top of that, these are all well within the orbit of Mercury. So they're very hot and they can't support life at least they don't support liquid water, so the life as we might know it. So these are not planets which we're going to be looking at life, but how did those planets form? How did they get into that configuration? And as I said, how do they get locked into a resonance? And this is a sort of a musical interpretation of that resonance to give you an idea how they're in lockstep as they go around. So as we're beginning to understand that sort of population of exoplanets around other stars, we begin to find that probably the majority of stars in our Milky Way galaxy, which you see again here from the summit of Paranal in Chile, that there are planets around many of those. But most of the ones we've discovered to date are planets relatively close into the star because of the techniques we've been using. But our mission Gaia, which has been in orbit since 2013, has been measuring the motions and distances of stars with extraordinary precision since then. And when I say extraordinary precision, effectively the level of motion that Gaia can detect as the stars slightly move through the sky, maybe wobbling because there's a planet going around the star. We're able to detect movements on the order of the width of a human hair at the distance of 2,000 kilometers. So that tiny precision in the motion of stars allows us to trace out the motions of the stars on the sky, and also, as I said, to find whether there are planets orbiting around those. And that's a big chunk of data that's about to be released this summer. The third data release from Gaia will have exoplanets in for the first time. So that's very exciting. There's a huge amount of science being done by Gaia, looking at our Milky Way and how the stars are moving around. Well, that tells us about how the Milky Way was put together. But just in the interest of time, I'm just going to show you this one lovely simulation based on data of how stars will move over the next 1.6 million years. And these are 40,000 stars with it very close to the sun. And that's how all of the stars are going to move around. This is an all-sky projection, so you'll see them curving at some point. That's a projection effect. But as we look at this, we see that all the nearby stars moving, buzzing across the sky at relatively high speed. Of course, tiny amounts of angular motion because they're very far away, but moving at kilometers a second throughout the solar neighborhood. Now, another mission which has been operating for a very long time, much longer than Gaia, is the Hubble Space Telescope, which was first launched in 1990. Has been serviced, had new instruments, new solar panels, new gyroscopes, and so on, installed on board in a series of shuttle missions over the decades. And so Hubble is still operational, still working extremely well, and of course has generated a huge number of scientific papers spanning the edge of the universe all the way into our solar system. Just one example is this giant image, a mosaic made of the Orion Nebula, perhaps turned on its side with respect to most images you've seen. But this is a visible wavelength image in which we can see this bright glowing gas surrounding the very bright stars in the very center, the so-called trapezium. But this only tells us a very small fraction of the story of what's going on in Orion. If we move into the near infrared, so wavelengths 5 to 10 times longer than the visible wavelength seen here, you can effectively penetrate through the dust, which is obscuring what's really going on in there, and also see the cooler objects, the young stars which are forming just maybe 1 million years old. And so this is a ground-based image of exactly that same region. And now we see thousands of young stars from 50 times the mass of the sun down to just 1% the mass of the mass of the sun. And objects called brown dwarfs, which aren't even the stars at all because they're not going to fuse hydrogen in their cores. And I'm going to be looking at this region very soon with a new telescope, which is designed specifically to work in the near infrared. So this is the Hubble Space Telescope, 30 years old and then some, in low Earth orbit. And this is the new kid on the block. This is the James Webb Space Telescope, where Hubble has a mirror 2.5 meters in size. JWST has a composite mirror 6.5 meters in size. And because it's designed for the infrared, you need to reduce the temperature of the telescope down to just 40 Kelvin, so minus 223 degrees Celsius, so that it doesn't emit thermally at the wavelengths we're trying to detect, between roughly 1 micron and 30 microns. And also, to get cold, we need to be as far away from the Earth as is sensible. So we're going out to this point where we are now, 1.5 million kilometers from the Earth, the L2 point. This is the real observatory on the ground just a few years ago. The main mirror, which you can see folded in its launch configuration, and then the sun shield, this tennis court-sized structure, which was unfolded here, this 5 layers of very thin metallized film to act as a sun shield to keep the telescope very cold. Of course, was all packaged up. And just as a personal note, I've been working on this mission for 24 years. I started in 98. And here's a couple of pictures of me before and after. So this is when I started on what was then called the Next Generation Space Telescope in 1999 at ESTEC. And this is the telescope in the background folded up at our French Guiana launch site just in November. And so you can see the mirror again folded up, and now the sun shield all packaged as well. Of course, this is a collaborative mission between NASA, the European Space Agency, and the Canadian Space Agency. We've built 2 of the instruments on board, and because it's at Kourou, of course, we provided the launch. And I'm now going to show you just a snippet of the launch, which took place on Christmas Day. And I was very lucky to be there to witness this from just 5 kilometers away, which is where you'll see the people standing in this short video now. Yeah, hugely emotional moment for many people, as you'll see.
6, 5, 4, 3, 2, unité, top.
Liftoff from a tropical rainforest to the edge of time itself, James Webb begins a voyage back to the birth of the universe. Punching a hole through the clouds, 20 seconds into the flight, good pitch program reported. Rocket continues to fly uphill in nominal fashion.
And as I say, hugely emotional. Maybe you spotted me there in the picture. But just a few minutes later, of course, we had this beautiful moment where the spacecraft separated from the upper stage and became free. And we had video on board, and I'm going to show you that. This is speeded up in the interest of time, so this is a factor of 5 speeded up. But you'll see the moment also when the solar panel deployed, which was also a hugely important moment on the way in this mission. You'll be able to see the thrusters on the upper stage burning, reflected in the base of the telescope on the left-hand side there. And that was to direct the upper stage away so that it didn't follow JWST out to L2. There's the solar panel unfolding and then glinting in the sunlight. This was over the Gulf of Aden, which you may have just seen there in the bottom corner. Of course, that's just the beginning for this mission, and what we've been doing for the last 5 weeks is getting the telescope unfolded, and you'll see here how that all goes, again with a little bit of music. So the first thing was to get that solar panel out, which you'll see that was 20 minutes after launch. And then unfolding the high-gain antenna to beam data back to Earth. And then the key thing was to fold down the sun shield. These pallets folded down on either side. And inside those pallets are then this 5-layer sun shield packaged up. And we move the telescope up by 1.5 meters to thermally decouple it from the spacecraft. And then that's a momentum flap at the back, which is a very important part of the mission as well. We pull the sun shield covers back, and then start deploying through cables and pulleys and motors, very slowly pulling out the 5 layers of the sun shield. And this, for many people, was the biggest risk, the moment where we thought if we were ever going to get into trouble, this would be it, past the launch itself, of course. Because there's a very analog structure here, and this had to be very well controlled, this pulling out of these very thin films, spreading them out to make them into effectively a radiator to get rid of the heat. And then you'll see the secondary mirror deploying over the top, and then finally the wings of the primary mirror moving around. The big radiator on the back there to cool the instruments down. And that all went perfectly. It's all happened. And now we're in the position where just in the next day or so, we're going to start taking images for the first time through the telescope. We'll have 18 images of everything we look at because the 18 primary segments are not aligned. We have 3 months ahead of us to try and align those mirrors to get them not only pointing all in the same direction, but also phased optically phased so that we get a fully diffraction limited 6.5 meter telescope. And that then enables us to do a huge range of science, which I won't go into, but we're going to be looking in the solar system, looking at the planets and moons outward from Earth. We can't look towards the sun with the observatory, so we'll never see Venus and Mercury, but we can see the outer planets and the Kuiper belt and beyond. We'll be studying planetary atmospheres, as I mentioned before, exoplanet atmospheres like this. We're looking in regions where there are young stars being born, looking at disks of material swirling around them, forming planets as we look at them. And that's an area I'm working with the JWST. And then at much higher, larger distances, looking at how galaxies are evolving over cosmic time. As we look further and further back, of course, we're looking deeper and deeper into time. And we're seeing galaxies changing because we're seeing them as they were billions of years ago. And one of the fundamental goals of this mission is to look back, all the way back to the first stars and the first galaxies that formed maybe 150 million years after the Big Bang. So just a blink of an eye after the Big Bang. And those galaxies, because they're so far away, they're so highly redshifted that all of their light is in the infrared at this point. So that's why you can't use Hubble to see them. That's why which is what this image is from. In 6 months or a year's time, we'll have images of these equivalent fields much deeper, much further away, and be able to see those first light galaxies. Now, not only is JWST launched successfully, but we're building new missions, which I'll talk about before we come back to the solar system. This is our Euclid mission, due for launch later this year, which is a smaller telescope, also in the infrared, doing a very wide field survey of galaxies to look at the formation of structures in the universe over cosmic time in a much more wide field way than JWST can. And therefore to look for the properties and investigate the influence of dark matter and dark energy, which affect the way that the galaxies have formed over time, even if we can't see that material itself. And other things we can't see directly, for example, certainly with the human eye, are X-rays coming from black holes, and that's the focus of our Athena mission. The hot material just before it spirals into a black hole gives off X-rays. That's under construction at the moment, a giant new X-ray telescope. And then the LISA gravitational wave mission, which uses lasers over 1 million kilometers between 3 spacecraft to sense gravitational waves from merging supermassive black holes throughout the universe. And we've proven the technology for that with our LISA Pathfinder mission. And we're now starting to build the full gravitational wave observatory. So in the last few minutes, let me come back into our own solar system, in particular, the exploration of Mars. So this is Mars as it is today, a very cold and very dry planet, mostly with CO2 polar hoods at the 2 poles. But we know that Mars, in its deep past, was much warmer and much wetter. We know there's a lot of evidence for water having been on the surface of Mars in the past. And one of the big questions is there evidence for water on Mars in the liquid form today? And a recent very tantalizing result came from our Mars Express satellite, which has been in orbit around Mars for almost 20 years already. And looking at one of the poles in particular, so this is a broad swathe across Mars. If we look at the South Pole, this is the North Pole on the left-hand side, we look down at the South Pole, and then we see the CO2 and water ice mixed there, but of course that's in the frozen state. But underneath the polar regions, we can penetrate with a radar system at 2 to 5 megahertz and go down to kilometers beneath not just the ice, but also the permafrost there. And in this particular region, a region called Ultimi Scopuli, what was discovered a few years ago was a large area of reflectivity in the radar signal that has been modeled as being from liquid water at minus 65, minus 70 degrees Celsius. And you'd wonder, how can it be liquid at those temperatures? Because it's completely perfused with perchlorates, so salt of some form. And that can keep the water at liquid, in its liquid state, even at those temperatures. So that's been passed around in the last couple of years, and there's some questions about it. How do you actually heat the water up, even to that temperature at the pole of Mars? And an alternate explanation is that it might be saturated hydrated clays, so not liquid water in the form of a lake, but clay, which was reflecting the radar. And that's exactly the same kind of clay as is found in cat litter, so-called smectite clays, which absorb a lot of water, which is why it's used in cat litter. So let's go back to Mars and to the place that we'll be going next with a mission we'll be launching later this summer. The ExoMars rover is finally going to Mars this summer to a place called Oxyoplanum. And we're going to zoom into this region, Chrysoplanitia, which is known to be a place where water flowed out dramatically across the surface, very catastrophically, billions of years ago. And if you look around that region, you see places where, from orbit, you can see there are places where there's clay on the surface in this case. And of course, clay forms in the presence of liquid water. So these are the places we want to go. And we'll be going to this region outlined in green, Oxyoplanum. We zoom down to the surface and see the land, where the clays are, and where the landing ellipse of the ExoMars rover will be, to be launched this September. And that rover, of course, is named for Rosalind Franklin, famously involved in the discovery of DNA, hence the connection to possibly to life. But the one capacity it has, which is completely unique over all other rovers flown to Mars, is that it has a drill on the front that can go 2 meters underground. And that's important because the surface of Mars is bombarded by ultraviolet light and ionizing radiation, and that destroys organic material. So even if life isn't there today anymore, if there was evidence for it in the past, we'd have to be looking for it deeper down. So hence the drill to go to 2 meters. The rover has been tried. The drill has been tried, as you can see, recently, drilling through rock as well as through clays. And another thing that we have on board, which is unique to stop us getting trapped, which happened to at least one previous Mars rover in a sand trap, is that we're actually able to walk the rover, not drive the rover alone. We can actually walk the wheels out of a sand trap. You can see the wheels rotating and spinning in the sand, but by gradually walking out, and this is of course speeded up, we're able to get out of sand traps, and that's a very important part as well. And of course, beyond that, what we're going to be doing is working with NASA on a mission going to this place in the bottom right corner in Syrtis Major, a place called Yezero Crater, where we know that there's fluvial pan. We believe in the deep past it looks a bit like this, a place with water, with volcanism, and potentially the situation, the potential for generating life billions of years ago. And so this is region close up. And the Perseverance rover landed there very recently, and that is now beginning to collect materials which will be returned to Earth when it's picked up by a fetch rover, and we'll be picking those samples up and returning to Earth for study in the Mars Sample Return mission. So there's Perseverance on the ground, drilling holes, collecting samples and dropping them on the surface. So the last thing I'm going to talk about now is the search for methane on Mars, because that's another potential tracer. So the Curiosity rover, which has been on Mars since 2012, has seen methane on Mars, and some of our other assets have. But our Trace Gas Orbiter, which landed there in 2016, it's been taking spectacular images of craters like this, but to date has seen no methane in the atmosphere, unlike what is seen on the ground and we've seen in other assets. And one of the thoughts is maybe it's diurnal, maybe we're only looking with the Trace Gas Orbiter in daytime and Curiosity's only seeing it at night. It gets destroyed in sunlight. Another possibility is that in fact we have the wrong models, that where we thought we were seeing methane before, it might just be previously unknown lines of carbon dioxide. So this is still up in the air. Is there methane on Mars? And is that methane, if it's there, is that biogenic? Is it being created by life under the surface? So that's still a very open question, whether there's methane on Mars. Well, there's one place there definitely is methane to finish, and that's on Earth. And to loop back to the fact that ESA is not only studying the solar system and the universe beyond, we're also spending a huge amount of effort studying our planet. This is Sentinel-5P, which in collaboration with a small satellite called GHGSat was seeing new sources of methane, probably leaking from gas wells in the Permian Basin in the United States and from factories in China. And of course, that's a real problem as a greenhouse gas. So it's something we'll be studying very much in the near future. And we've already seen on Earth greenhouse gas, methane, probably leading to the increase in noctilucent clouds. I never saw them myself at low latitudes until the last few years. This is a couple of years ago at ESTEC here in the Netherlands, all over the sky. And that's probably very directly linked to atmospheric methane. So it should be another wake-up call for us. Not only should we be studying the solar system beyond, but also paying a lot more attention to our own planet. These are those noctilucent clouds seen from the ISS in 2020. With that, I thank you for your patience. I've gone a little bit long, but hopefully still plenty of time for questions. Thank you.
Well, thank you very much, Mark. I'm almost breathless just watching your presentation. I'd certainly not realized the extent of involvement of the European Space Agency in the various missions. That's really quite something.
Thank you.
Right, we have a number of questions. The first one from Phil Wren goes back to your very first slides. He says, when a new rocket is launched, how do astronomers calculate the critical path through known satellites in orbit?
Well, indeed. When JWST was launched on Christmas Day, there was a window for the launch. Obviously, we needed to launch at a certain time of day in order to get in direction. We didn't go into Earth orbit. We went straight out on direction to L2. So the window wasn't that wide, but it was completely broken up as well by passage overflights of known satellites, including Starlink satellites. So we wanted to launch exactly on time. We did. But if we hadn't, if there'd been something and we had to wait 5 minutes, maybe we couldn't have launched at that moment, but maybe a few minutes later. And of course, we know where the big objects in low Earth orbit are because of radar. There are radar surveillance going on permanently. But there are objects at a smaller scale, at centimeter scale, where we have no idea what's out there. We just have a population. We don't know where they physically are. So the big satellites we can avoid, but the smaller stuff, not possible at all. I wouldn't say it's dumb luck, but the same was true with Solar Orbiter when we came through. We monitored the satellites that might be in our way on the flyby, and we could, if we had seen a collision that may have been inside our tolerance, we could have actually effectively diverted Solar Orbiter by a little bit about a day or so earlier. But within minutes, forget it. It's way too late at that point. So at some point you cross your fingers, and it's only getting worse, definitely, a lot worse. It's a major, major headache for our colleagues at ESOC, our European Space Operations Center in Darmstadt. They have seen collisions on some of our satellites, small debris particles. We had to move our big Aeolus satellite, our wind LiDAR. That had to be moved out of the way when a Starlink satellite was coming through. They phoned up Starlink, SpaceX, and said, would you mind moving your satellite? And they didn't even reply to the email. I think things have got better since then, but they're launching lots more stuff as well.
Okay, we have a question from Darryl Walmsley, referring to your Dragonfly wings. He says that he's been involved in some research looking at antibacterial surfaces and came across Sharklet. It's a micro-pattern film which inhibits bacterial growth without the need for chemicals. Are solutions like this being implemented on the ISS?
Well, that's exactly what this microtextured surface is, with copper combined with the etching, the laser etching. So I think there's no chemical treatment of that. It's just using the copper as the base material, and it's being tested on steel and on copper zinc as well. But fundamentally, it'll come down, we believe, to that micro grooving. So much again the same as the sharklet, the shark skin, that roughness. It's not for the same reason, of course. Sharks have that roughness. That's to break down the boundary layer. But in this case, we think, and you can take videos of bacteria ripping themselves apart as they try to move over dragonfly wings.
Thanks. Then we have a question from Nicola Fabry. And he's asking, which type of shielding do spacecrafts have to survive nearby solar corona?
Well, we use, for electronics, for example, we have shielding around the electronics, metal shields. But when it comes to I'm kind of ducking the question slightly. We use lots of different materials, but the one that we have on the front of Solar Orbiter, which is effectively just a heat shield in that case, so that's protecting us from the temperature. it's not a, let's put it this way, it's not a vegetarian satellite, because the material on the front is actually made up from charcoaled cow bones, a material which is extremely black. And you might say, well, you want to be extremely white to reflect, but of course, if you're white and reflecting, you're not actually radiating heat. So it turns out that in that context, the right material to have is something extremely black. That comes from a company in Ireland called NBio. So it's a mixture of shielding. You also need to be careful with missions like Solar Orbiter, because they're actually measuring very low level magnetic field and particle influences, and they need to be extremely clean themselves. So you can't just go bolting on, say, magnets, for example, to deflect cosmic ray particles, which you can use in other circumstances. In this case, you need very, very clean non-magnetic materials throughout the whole spacecraft. So it's a very complicated set of different kinds of materials. And as an astronomer, I'm less an expert there than you can probably follow up on our website to get more detail.
Thank you, Mark. There's another quick question from David Wellesby. If there was only the Sun and the Earth, presumably James Webb would be stable at the Lagrange point. How much does the Moon upset its position?
Well, the L2 Lagrange point is not actually a stable point. What we have, effectively, this is a solution to a three-body problem where the third object is very low mass. And in that case, the three bodies involved are the Sun, Earth, and JWST. So L4 and L5 are the stable ones. Those are out at 60 degrees around the Earth's orbit. And if you put a satellite there, a mixture of the gravitational forces and Coriolis forces will keep the satellite in place. And that's why actually asteroids, small asteroids, collect in the Lagrange point, in the L4 and L5 Lagrange points, at Jupiter in particular. But L1 and L2, so L1 is 1.5 million kilometers towards the Sun from the Earth, and L2 is the mirror on the other side. And effectively what happens there is as you try, if you're slightly further away from the Sun, you should go around the Sun in a slightly slower orbit than the Earth. But the Earth's gravity kind of tugs on you and keeps you in place, so you track around the solar system with the Earth. If you try to go a little bit faster, you'll get pulled back by the Earth's gravity. If you go a bit slower, you get pulled back. But if you go out from the Earth or into the Earth, then gravity is your enemy, because if you move away, the Earth's gravity isn't strong enough, you just fall away. If you move in, then you go towards the Earth. So what we actually have to do is go in an orbit around L2, a very big one, 1.5 million kilometers across. And that is actually much more stable than sitting at L2 itself. We do have to do course correction because the Moon perturbs us, Jupiter perturbs us, all sorts of things perturb us, and indeed solar pressure hitting the big sun shield perturbs us. But it's a very slow, long orbit, 6 months, and we can correct very well. That will be a life limiter, doing those trajectory corrections. Or fortunately, the Ariane 5 launch trajectory was so good on JWST that we saved a lot of fuel on the observatory itself, and we may have doubled the lifetime of the mission from 10 years to 20 just by having a super precise injection from Ariane 5. The other reason you don't want to be at L2 itself is you would be in the shadow of the Earth. You get no solar power if you're there, so you don't want to be blocked by the Earth. That's not a good thing. So being in this big orbit means we can get full-time sunlight on the hot side of the spacecraft, but permanently keep the observatory in the cold on the other side of the sun shield.
Thank you. We have a question from Gordon Doherty. It's quite a long question, so I'll try and just extract a part of it.
Okay.
Basically, he's asking, when will it be recognized that the primary force in the universe is electrical? That is, or is gravity still seen as the primary force, even though every electric universe prediction is shown to be correct, whereas gravity predictions are often found not to be?
I'm going to duck that question completely. Yes, I've talked a lot to people who are electric universe fans, and it doesn't work. But I'm not going. I won't go into it.
Okay, fine, thanks. Yes, I'm not quite sure how to pronounce this person's name. V. Walker. What is the purpose of the, he says, aft flap on the James Webb Space Telescope.
It's one of my favorite bits of the spacecraft. You would think as an astronomer, I'm a big fan of the instruments, which I am, and the rest of it. So the telescope has this giant sun shield the size of a tennis court, and the solar radiation acts on that and pushes on it like a light sail. Of course, that's a very small amount of thrust, but it's non-zero because it's a very big shield. The center of light pressure of the sun shield on the telescope is not coincident with the center of mass on the whole observatory. We try to put it as close as possible, but by the design it's not perfect. So there's an offset between the center of light and the center of mass, and that means that as the sun pushes on the shield, there's a torque, and the whole satellite will rotate. Now, we don't want that. We want to be stable, pointing at sources out on the other side. And we need to keep the sun shield from not going flat and letting the telescope back into the sun. So the way that we stop that happening is by having what are called momentum wheels on board. And those momentum wheels rotate in the opposite direction to absorb the angular momentum that's building up as the satellite wants to tip over. So you spin wheels in the other direction and everything stays stable. At some point, however, you get to the point where the wheels are spinning as fast as they can. And so you actually have to offload the wheels. And the way you do that is by firing thrusters, small thrusters on the hot side of the telescope. And in that case, trying to tip the telescope the other way, and you can unload the wheels to get them down to slow speed again. So what was done was to calculate where, on the ground, where we thought the center of light pressure was, and the center of mass as precisely as possible from all the measurements made of the spacecraft. And that aft momentum flap was deployed to just the right angle that should minimize the distance between the center of light and the center of mass. So to minimize the amount of angular momentum, the torque, and therefore the angular momentum buildup, and in turn limit the amount of fuel we have to use to offload the wheels. So that aft momentum flap is actually very important. If it hadn't deployed, the mission would have been much shorter because we would have been constantly using thrusters to offload the momentum wheels.
Right. Thank you, Mark. And from an anonymous attendee, is there a program to declutter space?
Well, there are various aspects to that. I mean, one of the things is that if you put things in very low Earth orbit, they come down through atmospheric drag. I showed you the Swarm satellite at the beginning. We've had other satellites of very low Earth orbit. They're actually they have aerodynamic shapes. And one of the moves that Starlink has made is to actually start putting its satellites at lower altitudes. That's good for their latency, but it's also good for removing satellites from orbit. But of course, there's a lot of other stuff up there. And as we launch newer things to higher altitudes, they won't come down for hundreds of years. So there's a real move now, real pressure to build deorbiting systems on board to bring stuff down and burn them up in the atmosphere. But then there's still many things which are floating around. And we've started a program called Clean Space, working with companies to actually go and catch material. It seems kind of counterintuitive to fly another satellite to catch debris. And it's not trivial. I mean, this isn't the film Gravity, where you can use a fire extinguisher to get from one orbital plane to another. There's lots of stuff in lots of different orbital planes, all moving at very high speed. So it's non-trivial to clean it. But we have to start somewhere, and it's important that we, at least the very biggest things, the things which have the potential for then creating huge swarms of material if they are ever involved in collisions, as we've seen more than once. So yeah, it's a legislative thing in part. It's a technical issue how you do it, and it's also down to the responsibility of individual operators. And there's an increasing amount of pressure to start getting that right, because everybody's heard of the so-called Kessler syndrome, where if you have a runaway cascade of satellites hitting each other, you can end up cleaning the whole of low Earth orbit out, and that's not a good thing for obvious reasons.
Okay, a question from David Robinson. JWST will collect the light passing through the exoplanet atmospheres. Will it be able to form any sort of fuzzy images of the larger exoplanets?
Yeah, it's more to do with how far away they are from the star. So we have a kind of what we call an inner working angle, which is the closest we get into this incredibly bright star. In any case, even if they're sort of naturally faint stars relative to the planet, they're always going to be very bright. So we have what are called coronagraphic spots. We can put a spot over the star and block that out, but that has a finite size, and so we can't get in very close. We can't get into the, say, the distance of Earth around a sun-like star at, say, 10 or 20 parsecs away. But much wider planetary systems, and we've already imaged some of those from the ground, we know they exist, those will be accessible to imaging. Ironically, unless they also pass in front of the star, they won't be so easy to get the data on for spectroscopy, because they're very faint. When they move in front of the star, you have the whole starlight streaming through the atmosphere, and that becomes basically your signal, and it's just the tiny absorption dips which tell you about the atmosphere. So we will be imaging some, but the great bulk of what JWST will be doing are these transiting planets close into their stars. The other reason for that is that to build up the necessary signal to noise, to get a good dip in the spectrum, you're actually going to have to observe lots of transits. The transits are pretty short. You don't get much signal to noise. And if they take years to go around, which means they're at very large radii, orbital radii, you just won't get many. So most of the targets will be these ones on few-day radius away from the few-day period. And then you can accumulate lots of orbits, lots of transits, and lots of signal to noise.
Okay, there was another question about exoplanets from Mr. Walker. As to observe an exoplanet transit a star, that star, the planet, and the Earth must all line up in the same plane. Is it just a coincidence that the exoplanet's orbits are in the same plane as the Earth, or is there something more going on?
Well, I mean, we don't see transits around the great majority of systems where we know that there are planets. So we can discover planets with other techniques, the so-called radial velocity technique, which watches the emission lines or the absorption lines in a stellar atmosphere change periodically as the star moves towards us and moves away from us. That happens in our own solar system. For example, Jupiter is the dominant source of other gravity in the solar system. And Jupiter and the Sun, Jupiter doesn't orbit around the Sun, they both orbit around a point which is inside the Sun, but not at the center. And so the Sun wobbles in the sky because of that reflex motion. And so we know from radial velocity surveys there are many planets at different angles, because that doesn't require to be in a particular orientation. But if you look at enough stellar systems, you will get some which, by chance, line up. What's the only thing to keep in mind then is when they're closer in, there's more of a chance that they will be in front of the star from more angles than if they're further away. The alignment works best. The chance of alignment is greater when they're close in. So that's another selection effect. It means we tend to find things which are closer in rather than things which are further away, along with the period being shorter, so we can see repeat dips and we can say that's a planet going around, rather than just seeing one and thinking, was that a planet, or was that just a stellar flare or a big sunspot, for example?
Okay, a couple of questions that have a slight sort of political edge to them. One of them is, what are your thoughts on private companies moving into space as opposed to organizations such as NASA and ESA? A challenge, an opportunity, or both?
Well, I mean, private companies have been in space forever because we don't build spacecraft. Companies like Airbus and Thales Alenia Space and OHB and others in Europe, they build our missions. Our rockets are sort of co-financed between European Space Agency and Arianespace. So that's private, and the same's true in the US. It always has been. Now, when we talk about completely private companies doing just what they want, so SpaceX and Starlink. Of course, a lot of SpaceX funding has come from the US government for Crew Dragon and for the cargo vehicles taking material to the ISS. So even they are not free of government funding. They're on a different financial model, but, does that make them private or any more than ULA and Arianespace? Perhaps not. I think where things become very different is where we lack a regulatory framework for making sure that everybody works together well. So this low Earth orbit problem is a very serious one. At the moment, there are regulations on who can launch what, who can use what frequencies, but there's no kind of upper limit on that. And there's no sense that we can say, well, once you've obeyed those rules, then you can fly what you like. It is becoming a concern for our traffic management and also space debris that perhaps we need some more regulation. When it comes to things like rockets going to Mars or rockets going to the moon. Well, we'll see. I mean, there's one thing that's different between civil space agencies and private space agencies, and I mean it somewhat cynically, is that we're taxpayer funded, and we have to be, at least as far as I'm aware, we have to be as straight and as honest and as open and transparent about what we're doing with taxpayers' money. When it's a private company, well, it depends if they're listed or not. It depends whether they have stocks on the stock market, what the rules are. But if they're not, what do they have to tell you? And how believable do they have to be about their projections and their timelines? It's not to say we launch everything on time, but we try to be as open as possible about why things take longer sometimes. So we use this private companies. We use SpaceX to send our astronauts to the ISS, to send equipment to the ISS. So we're not, against them in that sense at all. But I think we are in a time where we have to think quite hard about how to work in a more modern framework than the Outer Space Treaty allows. I mean, which is one example. If we are going to Mars and one of our aims is to look for life on Mars, then how do we regulate sending humans to Mars through private companies who might not, for whatever reason, care to worry about what we call planetary protection rules? And we saw an example of that with the Beresheet private mission to the moon a couple of years ago, where without telling anybody, they actually packaged some desiccated tardigrades, so life, and when it crashed into the surface, they were spread on the surface. Now on the moon, we don't believe that's a problem, but imagine that had been done on Mars. So we live in interesting times. Let's put it that way.
Yes, because Steve asked a related question, which you've probably answered, because he said, so how do enterprises get permission or approvals for launch of low Earth orbits?
Well, again, it's not very joined up, because one of the things is frequency allocation, spectrum allocation, and although we in ground-based and space-based optical astronomy see the light streaks, our radio colleagues see these satellites very brightly in what they're doing, because of course they're beaming signals backwards and forwards. And there is a concern there, for example, that some of the electronics on these spacecraft are very cheap relatively. They're launching thousands a year of these satellites, and they're willing to have some of them fail. And that means that they actually radiate electronically radio waves out of band, out of the frequency that they're supposed to be in. And this is a big concern for our radio colleagues. But again, there's no joined up sequence. There's the FAA for launching, there's the FCC in the US, but again, they don't speak for us. The ITU does speak internationally for frequency allocation. But yeah, it's become a major concern in recent years, and we're working, various of us are working with the United Nations, for example, so-called COPUOS, the Committee on the Peaceful Uses of Outer Space, to try to put a better legislation on this before it's too late, before we basically just said, well, we can't see the sky anymore at radio wavelengths or with astronomy from the ground. So yeah, we do need to work more at a joined-up legislative process. That's certainly not happening at the moment.
Right, we have a question again related to low Earth orbit, and saying, can we realistically expect any early warning of a Carrington-type event? Would any warning be too short to be of any value?
Well, typically the coronal mass ejections, they can be seen in visible light, of course, 8 minutes later. But what's often a problem are big sunspots coming around the edge of the sun, which we can't see from where we are at Earth. But we do have satellites, Stereo A and Stereo B, which are actually around the orbit from Earth, and they can see the sides of the sun, which we can't see from Earth. Solar Orbiter, interestingly, will be the first satellite to go out of the ecliptic and be able to look at an angle down towards the solar poles and take pictures for the first time. So there are a number of satellites which are involved in this. And the other thing which we can actually do, and we proved this a few years ago, is that we can see new sunspots rising to the surface of the sun before they even reach the surface and effectively break the surface. We can see them in what are called helioseismology signals. We can see the acoustic vibrations of the sun. We can measure that with our satellites. We can see the internal structure of the sun. We can see sunspots rising to the surface a few days before they get there. But a big Carrington event pointed at the Earth. I mean, what are you going to do? I mean, you could turn all the electricity off and turn all the substations off. But I suspect that wouldn't go down very well. But it's a very interesting question. We're trying to provide as much advance warning as we can. The other side is, what do you do if you do have that warning? We saw it in Montreal, I think. Was it in the late 80s, where there was a much smaller event than the Carrington event, which knocked out a lot of substations in Montreal and down the east coast of the US. And there was a big blackout for days in Montreal as a consequence of the substations just being overloaded. So, yeah, it is a big issue.
Question coming back to the James Webb telescope. Will JWST be, this is from Kevin, will it be searching for Milky Way's rogue planets?
Yes, I'll be looking for them. Well, not in quite maybe the way you're asking, Kevin, but so we know that there are many planets which orbit around stars, exoplanets, planets in our own solar system. The question is, are there objects, the mass of planets, and I'm being careful, so let's say the mass of Jupiter, the mass of Saturn, which exist freely floating in our Milky Way. And there are two possible origins for that. One is that they have formed in spiraling around stars, like our own solar system, but in an encounter between two stellar systems, the gravity can then fling out the planets and they become free floating. The other way they can form is just be collapsing out of gas clouds themselves in the same way that stars do and brown dwarfs, but much, much smaller. So what I'm going to be doing with JWST is looking in the Orion star-forming region and looking for these extremely faint objects, so not going around the stars, but freely floating. And they could, in principle, the sensitivity we have with JWST, and we can't do it from the ground, takes us down to about the mass of Saturn. And if we can then measure the spectra of those objects as well, then depending on what we see in the spectra, we may have some clues about whether they formed in a stellar system or whether they formed in isolation. We don't know yet. That's why we're going to investigate. But whether there are huge populations of rogue planets floating around, we know of some of them from microlensing experiments, but we really don't have great constraints on how many such objects there would be. Some people think they might be the dark matter. We've pretty much ruled that out. Dark matter probably cannot be planetary mass objects floating around in the Milky Way.
Okay, we've just got a couple of minutes left, and there's just one comment and then a final question. Jerry Stone makes the comment that he believes, someone's just asked another question. He believes that the Sun-Jupiter barycenter is actually above the surface of the Sun, out in space.
I'll check. I had it in my head as being inside, but I can check. Yeah, I mean, it's certainly not very far away if that's the case, but we should probably be able to do the experiment. It's very simple. What's the mass ratio of Jupiter to the Sun? And then what's the orbital distance with respect to the Sun? But yeah, if I'm wrong, I apologize, but we can go and check it, that's for sure.
Okay, then a final one, which is another sort of political one. I think I know the answer, but Tim asks, has Brexit affected the UK's involvement in the European Space Agency?
Well, I've spent a lot of time working in Germany, and a word which I like is Jein, which is yes and no. ESA is an independent organization from the European Space Agency, so the UK is still a full member of the European Space Agency and contributes to various programs. Now, when I say various programs, there are two parts of ESA which are important to delineate. We have what's called the mandatory part of ESA. So if you join ESA as any country, you have to be in the science program, which is where a lot of the missions you saw this evening. So JWST, BepiColombo, Cluster, and so on. And the amount of money you put into that is it's negotiable en masse with all countries, but it's a fraction of your GNP. The other programs are what we call optional, where countries can join in other things in an a la carte way. So the human and robotic exploration, for example, astronauts and going to Mars, that's an optional program. And the UK is a part of the Mars program, a significant part, and now part of the human spaceflight part on the ISS, but less so, for example, than Italy, France, and Germany. There are programs, however, which are funded by the European Union, which we also build. And the two key ones are Galileo, the global navigation satellite system. So what many people think is GPS, but Galileo's separate, a more precise system. It's on most of your phones by now. You're using it without knowing it. And then Copernicus, which is an Earth observation system, where I mentioned the Sentinels, for example. And now that the UK is no longer a member of the European Union, it can't participate in those programs, and its industry can't participate. The Copernicus data are free to everybody to use in the world, so you can still get access, but your industries can't build those satellites. This is still under negotiation, under discussion. It's tied up in the Northern Ireland Protocol and many other things, so it's a bit of a mess. The Galileo system, what the UK is now locked out of, is what's called I forget the exact acronym, but it's a protected system, which is a secure channel used in times of emergency, which only EU member states can get access to. It's not more precise than the rest of Galileo, but it's encrypted, so it can be used for emergency services and also in wartime. So yes and no. I'm British. I still work for the European Space Agency. It's definitely affected my personal life in many ways. Things are very different now working in Europe than they were a few years ago. And there are programs which the UK cannot be part of. So, to be political, I think it's a grave mistake, and I think the UK will come to regret it. But we see that every day, perhaps. But I won't go any deeper on that.
Okay, well, thank you very much, Mark. I mean, if you look at the chat window, it's full of thanks and comments such as fantastic presentation and so on. So I think I'm sure our audience has found it a very enlightening experience. So thank you very much, Mark.
My great pleasure. I don't know if it's actually, is it possible to copy? I don't know how Zoom works. I've been using Zoom for 2 years. Can you actually log those comments? Always nice to see. But if there were any other questions,
I'll see if we can get them extracted. So,
thank you.
Right.
Yeah.
And we're out of time. So on behalf of the IET Sussex Network in particular, and all our members and all the audience this evening, Mark, I'd like to thank you very much for that a really fascinating presentation and your ability to answer all those questions.
Well, who knows? Maybe we can do it in person at some point before too long. But
yeah, we look forward to that, certainly.
Okay.
So thank you again, Mark.
My
Thanks
pleasure.
for your time. Right. Good night.
Good night. Bye-bye, everybody.